Hi there, so today we are talking about the moment of inertia of an object. So first of all, what is the moment of inertia? Well, it is a measure of how the mass of an object is distributed about its axis of rotation. It can be represented by the term I. Now it is crucial to understand that the moment of inertia affects how the object will behave in rotational motion. It is not a fixed value, like mass. In a rigid body, the value I changes as you choose different points about which the body is rotating. Now let's look at the equation for rotational motion of a rigid body. For a body in rotational motion, the equation is the summation of all external moments or torques on the left hand side is equal to I, which is the moment of inertia, times alpha, which stands for the angular acceleration in radians per second squared. Now let's see how this equation can be applied. Here we have a rigid body diagram. This body is rotating about its center of mass g. Now the total moments about the center of mass g is the product of the moment of inertia ig times the angular acceleration. Okay, so let's look at another case. Here we have another diagram. In this, the rigid body is rotating about another point called O. Now this point is fixed. So the total moments about O can be surmised as the following. It is the product of the moment of inertia about O times the angular acceleration alpha. So as can be seen, the rotational motion of a body not only depends on its mass, but also on how the mass is distributed throughout the body. In this case, the figures IO and IG represent that. If the body rotates about the point O, then we use IO. If the body rotates about its center of mass, in this case G, we use IG, as in the previous example. Now let's look at this in a little bit more detail. Consider a system composed of individual point masses, and the system is rotating about the point O. O is the axis of rotation. Ri is the position vector of mass Mi from the axis of rotation. Therefore, to find the moment of inertia about the point O, meaning Io, the following formula will have to be used. The summation of the point masses times the distance from the axis of rotation squared. Now let's look at an example question. Two masses are connected by a massless rod, and the system rotates about the midway point of the rod, O. Calculate I about the axis of rotation. So we're looking to find IO about the axis of rotation, which is O. Okay, so we use the following formula. IO is equal to the summation of the masses times the distance from the axis of rotation squared. So therefore, the first part of the answer would be 1 times 0.5 squared. Now, where does that 1 come from? Well, that 1 comes from the 1 kilogram mass at this end of the rod. The 0.5 comes from the distance between the mass and the axis of rotation. The final value is squared, so it's 0.5 squared. Now, for the second part of the answer, be plus 2 times 0.5 squared. Now that 2 comes from the 2 kilogram mass at the right end of the rod, and the 0.5 again, the same distance from the axis of rotation, which gives us a final answer of 0.75 kilogram meter squared. Okay, so that's how you solve a question composed of individual point masses. Now consider how would you find the mass moment of inertia for a continuous body. Consider a uniform beam of rectangular cross-section. Find the moment of inertia of the beam if it is rotating about an axis through its center of mass. We no longer have discrete point masses, but mass is distributed throughout the body. The formula is the following. As with the center of mass before, the sum is now replaced by an integral. And individual masses are replaced by mass elements called dm. An element of mass dm has the length dr. It is at a position r from the axis of rotation. Now dm can further be defined as rho dv, which is equal to rho times a times dr. Now if we go back to the formula we had above, I is equal to integral of mass times r squared times dm, we can now change it to integrating with respect to length. R squared remains the same, whereas dm, the expression we found over here, has now been replaced with rho a times dr. The center of mass corresponds to r is equal to 0 over here. Hence the limits of integration are from negative ln2 to ln2, as can be seen. Therefore the equation for the moment of inertia becomes the following. Now basic integration is undertaken. When the integration is fully completed, we end up with this expression over here. Rho times a times L cubed divided by 12. But the total mass of the bar is m is equal to rho v is equal to rho al. Now what does this mean? This is the equation we ended up on the last page. As you can see, rho a l are all present here. Now if we substitute m in for rho al, we end up with the following formula. I is equal to mass times the length squared over 12. This is the moment of inertia of a uniform bar rotating about its center of mass. Now this formula holds true for any uniform bar rotating about its center of mass. Okay, so next let's talk about the parallel axis theorem. Parallel axis theorem is used when the axis of rotation may not pass through the center of mass of an object. Also, the object is rotating about a fixed pin at O. The formula is as following. IO is equal to IG plus MD squared. In this case, IO is the moment of inertia of the object rotating about point O. IG is the moment of inertia of the object rotating about its center of mass. M is the total mass of the object, and D is the distance between the two axes of rotation, O and G, squared. There are two rules that need to be followed before the parallel axis theorem can be applied. The first, the two axes of rotation must be parallel. Given the moment of inertia about one axis, you need to be able to calculate the moment of inertia about a parallel axis. The second rule, this formula only holds for the axis about the center of mass. To go from one non-centroidal axis, say IA, to another, IB, you first need to go from IA to IG, and then from IG to IB. Now let's look at a quick example about the parallel axis theorem. Moment of inertia of a beam about one end. We first list the parallel axis theorem. IO is equal to IG plus MD squared. Now IG we've already found above for a beam. It's mass times the length squared divided by 12. MD squared turns out to be mass of the beam times the distance between IO, the point O, and the point G. which ends up being L divided by 2, which simplifies to IO is equal to mass times length squared divided by 3. So the moment of inertia about point O is equal to mass times the length squared divided by 3.